Question number 10 states that a block of mass m slides on a frictionless table. It is constrained to move inside a ring of radius r, which is fixed to a table. At t equal to 0, block is moving along inner circumference of ring with a velocity v naught. Coefficient of friction between block and ring is given to be mu. We need to find the speed and position of block as a function of t. So let's move and see the solutions.
Yeah, initially actually they have given the upper view of the table. So initially the block, let us assume the block is at position A, and at any instance the block has moved to point B and traversed an angle theta.
Okay.
And the given it is radius is r. Let the velocity at position B, let velocity at position B is equal to v, and initially it is given the velocity of body at position A is
v naught.
v naught. Velocity at position A is equal to v naught. So now let us consider the free body diagram of the body at position B. As we know, force as the table is having,
there is a coefficient of friction.
Yeah, there is a coefficient of friction to the circumference of the table. So as the instantaneous velocity is in this direction at position B, the force will be in the opposite direction for the body, and the normal reaction will be perpendicular to the instantaneous velocity, and we know it is moving in a circular motion. It will be having a centripetal force that will be equal to mv square by r.
Okay.
So writing the force equation, we will be having
the block is assumed to be massless.
No.
So
let the mass of the body be m. Actually here m is the mass of the body. So normal reaction is equal to mv square by r. Here there is no sort of gravitational force, because this is the upper view of the body. The gravitational force will be acting downwards.
Okay,
it will be always
into
acting
the paper.
Yeah, it is like into the paper. So the normal reaction will be equal to mv square by r, and as we know frictional force is equal to mu into n. This will be equal to mu into mv square by r. As it is given the force, as we know the friction is a non-conservative force. Here by definition we know F is equal to, for the non-conservative forces it will become minus F, that will be equal to minus mu mv square by r. That is equal to ma. So we will be getting A is equal to minus mu v square by r. As we know A is equal to dv by dt.
Right.
So just by equating this equation and this equation, we get dv by dt is equal to minus mu v square by r. Just exchanging the positions of v and r, we get dv by v square is equal to minus mu r by dt.
Correct.
As we are assuming it is starting from t is equal to 0 to t, and initial velocity from v naught to v, we will be getting integrating from v naught to v, dv by v square. As mu and r are constant, we can take that of integral, and this is from 0 to t. We just integrate this. We'll by solving this equation we will be getting 1 by v is equal to mu t by r minus c, and from t is equal to 0 to t is equal to t, and this is equal to v naught to v. By solving this equation we will be getting 1 by v naught is equal to minus c, that is equal to c is equal to minus 1 by v naught, and from this equation we will be getting 1 by v is equal to mu t by r plus 1 by v naught. So from this equation we actually got
the velocity in
terms of
t.
It is asked to find the speed. So the first part of the question is solved. So we can now let's go to the second part. We here got 1 by v is equal to mu t v naught plus r by r v naught.
Right.
We can write this as v is equal to r v naught by mu t v naught plus r. As we
Correct.
know, v is equal to ds by dt. Just by equating both the terms, we get ds by dt is equal to r v naught by mu t v naught plus r. So we'll be just integrating from 0 to s. As he asked the distance position of the block from point A, we are calculating this in terms of distance. So
Okay.
initial distance is 0 and the final distance, let us assume it as s, and also the initial time is 0, and for a particular time we are taking, let us take this as t. We get 0 to s ds is equal to r v naught by mu t v naught plus r.
Right.
Integration from 0 to t dt. After integrating this, we will be getting s is equal to r v naught by mu v naught into ln mu v naught t plus r by r. V naught gets cancelled, so we will be getting s is equal to r by mu into ln mu v naught t plus r by r. If you want the angular distance, just by considering, if you want the theta, just by taking this radius as 2 pi r, radius as r and the circumference as 2 pi r, and the angle traversed is 2 pi, we can just by substituting the terms 2 pi r for s and
Right.
theta is 2 pi, we just by manipulating, interpolating the things, we get angular displacement theta.
So we can express it in terms of linear displacement or in terms of angular displacement,
Yes.
just by simple substitution.
Yes.
So as we saw in this question, we have taken the position of the block at two different times. We have drawn the free body diagram of the block at a later time and calculated the force which was acting on the body, which was contributing to the centripetal acceleration. We found out the acceleration of the body and we wrote A as dv by dt, since we had to express the velocity in terms of the variable t. Once we found out the velocity, we substituted v as ds by dt, and in the end we got an expression for both the speed and the position of the block as a function of the time variable t. So let's look at the problem statement for question number 11. A figure is shown below. It says a skier plans to sky a smooth fixed hemisphere of radius r. He starts from rest from a curved surface of height r by 4. We need to find the angle theta at which he leaves the hemisphere.
Yeah, in this case, first let us take this height for initial position as b, and where the skier leaves this hemisphere as b.
Okay.
Initially the person is at height r by 2 plus r, because this is r, and at both the top of the hemisphere this is r by 4. Initial height of the person is at height r by 4. Initial height of the person r by 4 plus r, that is equal to 5r
5
by
r
4.
by 4.
Now just let us consider the persons as the body, and let us consider the free body diagram of the person at point B, where he just leaves the surface. The condition where he just leaves the surface is n is equal to 0, that is normal reaction is equal to 0. At position B, he is having gravitational force downwards, that is equal to mg. As given mass of the body is m, and g we know acceleration due to gravity, it is equal to mg.
Right.
And as he considered this angle as theta, so this the component this side, it will be equal to mg cos theta, and the normal reaction will be acting perpendicular to the surface, that is equal to n. As we know, he is moving in a circular, as this is a hemisphere, this will be a circular motion, and the centripetal force will be equal to, if we consider the velocity of the person at point B is equal to v, the centripetal force will be equal to mv square by r. So
Right.
in this free body diagram, just writing the force equations, we get mg cos theta minus n is equal to mv square by r. As we know, when the person is leaving the surface, n will be equal to 0. That implies mg cos theta is equal to mv square by r. Let us just name this equation as equation 1. So now consider the energies of the person at position A and B. At position A, he is initially having a velocity 0, so the initial kinetic energy will be equal to 0, and the potential energy, as he is at a height phi r by 4, initial potential energy will be is equal to mg into phi r by 4.
Right.
At position B, he is at a height, as in this triangle, this is r and this is theta, so this will be is equal to r cos theta. So he is at a height r cos theta. At position B, potential energy final is equal to mg into r cos theta, and as we assume the kinetic and as we assume the velocity of the person at position B is v, final kinetic energy is equal to half mv square. According
Fine.
to conservation of energy, we get initial sum of initial energies is equal to sum of final energies, that is equal to 5 by 4 mg by r is equal to half mv square plus mg r by cos theta. And from the equation 1, mv square by r is equal to mg cos theta, so that is equal to mv square is equal to r mg cos theta. By putting this in this equation, we will be getting 5 by 4 mg is equal to 3 by 2 mg cos theta. Just I am skipping these steps.
Correct.
This will be equal to 5 by 2 is equal to 3 cos theta. That will be equal to cos theta is equal to 5 by 6. So at an angle, cos theta is equal to cos inverse of 5 by 6. He will be just skidding out of the hemisphere.
So as we have seen in this question, again the concept that when a person leaves, when any body leaves the surface, then what we need to consider is we need to make the normal reaction at that instance of time equal to 0. So this was the concept which we studied in an earlier question as well. And then we have simply used the conservation of mechanical energy, since the surface is assumed to be frictionless, and we have taken the initial energy and the final energy and equated them and found out the angle at which it leaves the hemisphere. So let's see problem number 12. It says that a sphere of mass m hits the surface at angle alpha to the horizontal with a velocity v1 and comes back at an angle beta to the horizontal with a velocity v2. It's given that the surface has a kinetic friction coefficient of mu k. We are asked to find the value of mu k. So what would be the approach we should follow in solving these kind of problems?
Yeah, first thing we need to consider is the normal reactions acting on the body. Initially the velocity is in this direction, and that is
Right.
equal to v1, and the final velocity after just hitting the surface of frictional force surface is v2. When these type of problems occur, we generally attack these type of problems in terms of xy axis.
Okay.
So for velocity v1 bar, this component will be v1 sin alpha, and this component will be v1 cos alpha. As this is in the negative direction, we will be getting v1 bar is equal to v1 cos alpha I cap minus v1 sin alpha j cap.
Right.
And similarly for v2, just after hitting the surface, this is v2, and the components will be v2 cos beta and v2 sin beta. So v2 bar will be equal to v2 cos beta I cap plus v2 sin beta j cap. So we will be writing the forces also in the similar way. Forces is equal to when the body just hit the surface, we will be having the frictional force,
Okay.
gravitational force, and also the normal reaction. At the instant where just it hits the surface, normal reaction will be very high compared to mg, so we don't
Okay.
consider the mg in the force equation. And we know F is equal to mu into n, normal reaction. As for frictional force is acting in the negative direction, we will be having minus mu n I cap plus normal reaction in the upward direction, so this is equal to n j cap.
Okay.
Yeah, and we know instantaneous change in momentum is equal to force into dt.
Correct. By Newton's second law.
Yeah. So from this we just equate the from here, let us name this as equation 1, and from v1 and v2 we can get dp. So what dp is, taking m as the common thing, so directly I am writing the equation m into v2 cos beta minus v1 cos alpha I cap plus m into v2 sin beta plus v1 sin alpha j cap.
So this is the change in the momentum.
Yeah, this is the change in the momentum of the body at the instant when it just hit the surface.
Okay.
So F bar dt, we got minus mu n I cap plus
NJ. cap.
n j cap into dt. Just by equating the terms of I and j, we will be getting n dt is equal to m into v2 sin beta plus v1 sin alpha
Okay.
and minus mu n dt is equal to m into v2 cos beta minus v1 cos alpha. So let us just name this as equation A and equation B. By dividing B by A, we will be getting minus mu is equal to v2 cos beta minus v1 cos alpha by v2 sin beta plus v1 sin alpha. Just taking the negative out of both sides, mu is equal to v1 cos alpha minus v2 cos beta
Right.
by v2 sin beta plus v1 sin alpha. So this is the mu k, kinetic friction of the surface.
So as we saw in this problem, these kind of problems appear to be slightly complex, but if you approach them, if you attack them in the right way, it's just a matter of few simple equations and then manipulating the equations to get the final answer. So we calculated the initial velocities and we wrote them in terms of the Cartesian coordinates for both the initial and the final velocities, and we found out the force just at the point at which the particle it hits the ground. Then we used Newton's second law of motion to equate the force which acts on the body just the moment it hits the ground with the change in the momentum occurring in the body, and we equated the similar coordinates and we ultimately found out the value of the kinetic coefficient of friction.
Actually we mentioned here kinetic coefficient of friction because this is just due to the change in the momentum, so we consider it as the kinetic, not static.